Superposition. So we have covered source transformation theorem. We then moved on to Thevenin and Norton's theorem. We're now on to superposition theorem. So what exactly it is? Superposition says that circuit with multiple sources can be solved by following these steps. The first step is to set all the sources to zero except for one you want to consider. Okay, so I want you to focus on this graphics right here. You have a circuit. Okay, you have this circuit over here. You notice that it has two sources. There's one source over here, VS1. This is one source over here, VS2. What you are going to do, you are actually going to have one source at one time and then analyze the circuit. Basically, what superposition is that you individually measure the impact or influence of each source and their contribution to the circuit, and then basically just add up all the contribution to find out the voltages, currents across each parameter. So you'll do analysis having this battery, and then we will remove this battery over here, so just shorting it and then restoring this battery over here, and then do the analysis, and then basically adding these values right here, and then coming up with the uh, the voltages, the readings for the currents and the voltages. So the first step is to make sure you put everything to zero except for one source that you want to consider. You then apply KCL or voltage divider or KVL, and you solve for voltage currents across each circuit element using only that source. You repeat step 2 for each source. Remember, there are two sources here, but you may have more than two sources, so you keep on doing it one by one. And then the last step is to superimpose the contribution of each source upon each circuit element, and then finally the sum of all the contributions calculations. So we have this circuit over here, and we are going to analyze this circuit. I'm going to put label on this circuit. So say um, this is my R1 right here. I have my R2 over here, my R3, R4. Okay, and I'm going to simplify this circuit. Okay, remember the first step was to get rid of one of the source. So again, I have two sources here, one of the sources over here, and then I have a current source over here. I'm going to get rid of current source over here. So removing current source, which would mean that this circuit will then be equivalent to saying you have a voltage source, you have R1, R2, you have R3 here, you have R4 here, you have current source is going to be removed. So you know that when you remove the current source, you just basically open the circuit right here, correct? Okay, now remember you got R2 over here. So the first thing we need to do, just like we did in Thevenin theorem, that we need to find out the equivalent resistance for this network. And remember, this is going to be the 60 volts right here, the power supply over here. Okay, so looking at it, we realize that R3 and R4 are in series here, right? Uh, this over here and this over here are in series. So I can transform this circuit as like this. You have R1 here, R2 over here, and then R3 and R4 will add up. So I get R3 plus R4 here. Okay, so R3 plus R4 will equal what? R3 is 12 ohms, R4 is 8 ohms. So I get 20 ohms over here. Okay. Now notice here, R2, this over here, is in parallel with this resistor over here. Okay. So let's do that now. And I'm trying to do it step by step so you can just follow along. So the next step would be that R2 is parallel to R3 plus R4, correct? So R2 is how much? R2 is 4 ohms, 4, and R3 plus R4 is 20. So that would be 4 times 20 divided by 24. 20 plus 4 is 24. So that gives you 80 divided by 24. And that would mean you basically get what? It's going to be equivalent to 3.33 ohms. Okay. So I can then further transform this circuit to something like this. I have the power source, voltage source here. Okay. I have the R1 here. And then this over here is basically R2 parallel with R3 plus R4, which we calculated came out to be 3.33 ohms. We also know that R1 is actually equivalent to 5 ohms. And then if I add these two resistance, I basically get the equivalent resistance, total resistance, or yeah, so that will be total resistance 5 plus 3.33 ohms, and that gives me 8.33 ohms. If I wish to calculate the total current in this, so that current will be V over RT. V is 60 volts here. RT is 8.33. So that gives me a total current of 7.2 amps. Okay. So this is going to be flowing in this direction and it's going to be 7.2 amps. Correct? Okay. Now also notice here what we are trying to do here is we are trying to find the current across each resistor here using superposition, and also find voltage potential across nodes A and B. So this is going to be your node A, okay, and this is going to be your node B. Now let's move forward. Notice here that you will have at this node over here, you will have a voltage of 60 volts, okay? And your VA is going to be equal to this voltage 60 minus the voltage across this resistor over here. Okay, we already know the current that's flowing here is 7.2 amps. We just got that right. So this is going to be 7.2 amps, right? The total current that's flowing. So I can simply apply Ohm's law here. VA, which is this right here, VA equals to 60 volt minus the voltage drop across R1. I current over there across that resistor is 7.2. The value of the resistance is 5. And if I do the math, I basically get 24 volts here. Okay. So now I have the VA, which is 24 volts, and I can just write it down here 24 volts here. Okay. Remember, at this element, the voltage is also going to be 24 volt. Okay. I know the resistance. I can find out the current then. Okay. So let's find out the current. And I'm going to say this current is going to be flowing in this direction, correct? It's going to be flowing in this direction, and I'm going to label it as I2. Okay, so I2 equals to VA over R2. If I put those values in there, VA being 24, R2 being 4 ohms, so I2 gets 6 amps. Okay, all right, and remember the direction of this current is going to be downward. Having these directions is important because remember, at the end we are going to add the influence of each of the source. Okay, so having this arrows is extremely important. Now also know, now that we know that this current, this is the total current, which is 7.2 amps, and also this current that's flowing through the R2 is, say I can change the color if I can. Yeah, so that is going to be 6 amps, right? 6 amp going to this resistor. So which means 7.2 minus 6 amps, 1.2 amps goes through this resistor, 1.2 amps, correct? All right, okay. Now that we know that, we can find out VB here, okay? The voltage across R3 is actually the potential difference between VA minus VB. So I can write it down over here. The V3, which is the voltage across R3, is actually equals to VA minus VB over resistance R3, which is 12 ohms. Okay, VA is known. We have to find VB. V3 we can find out because now we know the current flowing through it. So V3 is going to be I3 times R3. I3 is how much? I3 is 1.2 amps. Also, I can write down here, I3 came out to be 1.2 amps and it's flowing in this direction. Okay, so 1.2 times R3, which is 12 ohms. Okay, 12 ohms. We have 12 ohms times 1.2. You do the math, you get what? So the voltage across R3 is going to be 14.4. Now, coming back to this equation right here, now I know V3, so that would mean I'm looking forward to find VB. VB will equals to, VB will equal 12 times V3. Oh, remember, this is going to be I3, right? So I3 equals to VA minus VB over 12, correct? Okay, so we are trying to get an equation for VB, which would mean 12 times I3, 12 times I3, and then you're gonna have minus VA, and then this will be minus here, okay? So if I rearrange it and I do the math, remember, I can actually put the value of VA here. VA was how much? VA was 24, right? So here I can write 24 minus 24, and then also I3 here is 1.2 amps. So I get 1.2, okay, minus sign will carry. And if I do the math over here, VB will come down to 9.6 volt. Okay, it's going to be in plus. Okay, so 12 times 1.2 gets you 14, 14.4 minus 24. So negative 9.6, negative 9, negative negative on each side cancel out to get VB equals to 9.6. So coming back to the circuit, this over here, which is VB, is equals to 9.6. Okay, remember, same voltage will go through resistor R. So I can simply apply Ohm's law here and find out the resistor current across resistor 4, and I'm going to label it as I4, and it's going to be VB over R4, VB being 9.6, R4 is 8 ohms, and if I do the calculation, it's going to be 1.2 amps, okay? And remember, the direction of this current is going to be, because, yeah, you have the higher potential over here, so it's going to be actually going downward like this, right? Um, and that's because there's no current, right? So here, so we're gonna go this route. Okay, all right. So is there anything else that I had to do? I got the I3, I got I2, I got I1, I4. I also got VA and VB. So let's just go ahead and put these value in this box right here. Okay, remember your R3 and R4 were in series, so in series current remains same, so the current across R3 and R4 is same. Okay, and also I4, if you look at it, the direction is going to be downward like this, so I'm just gonna have this arrow next to it. Okay, all right, now let's move on to the second part of the analysis, where I'm going to get rid of this source and then restore the current source. Okay, so, and if I'm going to go ahead and make that circuit, so the equivalent circuit to that would be, when we get rid of the power source, voltage source, we basically replace it by a short, right? We short it. So that's how you short it. You have then R1, which is 5 ohms. You then have R2, which is 4 ohms. I'm just gonna label them. You have R3 here. You then have um, R4 here, which is 8 ohms. And then finally, you have this current source, which is 5 amp. Okay, so the current is flowing in this direction, goes this way, goes this way, goes this way, and then goes this way. Yeah, so some of it will go here, some of it will go here. Um, Now we're going to do the same thing. We're going to have to find out the equivalent resistance, and we see that R1 and R2 here are parallel, this right here. So let's get that going first. R1 parallel to R2. R1 is 5 ohms, R2 is 4 ohms. So 5 times 4 divided by 9, 20 divided by 9 gets you 2.22 ohms. Okay, so if I need to transform this circuit, it will look something like this now. Here's your power source, which has been shorted. Then you have this resistor R3. This one was R1 plus R1 parallel to R2. You have then R3, which is now in series with it. Okay, This is your R4 here, okay? And then you have this current source, the independent current source, 5 amps. Remember, current is going to flow. Some of it will go here, some of it will go here, and then this is how it will go. Okay, now the next thing we can do is add these two resistors, right? So R1 parallel to R2, and then we can add plus R3, so we get what? 2.22 ohms plus R3 is 12 ohms, so I get 14.22 ohms. Okay, so if I further simplify the circuit, I get this. Okay, you have this 5 amp source here. This is your R4, and this is your R1 parallel to R2 in series with R3, and we just did the math. It came out to be 14.22 ohms, and R4 is how much? 8 ohms, correct? Is 8 ohms. Okay, we can go ahead and further simplify it. Notice that you can also, this is a Norton equivalent form too, so you can also apply current divider to measure the current across this resistor over here and also this resistor over here. Okay, so I am going to do that actually. So I'm going to start with measuring the current across I4. I4, we know the equation is I4 equals to total current, which is 5 amps in this case, times the total resistance. Remember, the total resistance is what? 1 over this value right here, which is 14.22 plus this 8 ohms right here plus 1 over 8, and then the inverse of the whole thing. So if I do the math, RT will come out somewhere close to approximately 5.15 ohm. Okay, all right, so times RT divided by, let me write it down in a symbolic form first. So this would be IS, the supply current from the independent source, times total resistance divided by the resistor across which you are trying to find the current. In this case, that is this R4 right here. It's R4 right here. So it's going to be R4. Let's plug in the values. IS is 5, RT is 5.15, and therefore, and also R4 is 8. So I get I4 to be equals to 3.2 amps. Okay, not to forget the direction of that current is going to be upward, right? So it's going to go like this and then go like this. So this is your I4 here, correct? It's going to be in upward direction. Okay, let's now move on to finding the current across this resistor right here, this one right here. Okay, so notice here, if you have 5 amps coming in, okay, and then I4, which you just calculated is 3.2 amps, 3.2 amps is flowing in this direction, then the current flowing in this direction is going to be 5 minus 3.2, which is going to be 1.8 amps, okay? So the 1.8 amps is flowing across this resistor over here, okay? So which would mean, so here you have 5 amps. This here, this is going to be 3.2 amps, okay? Here you have 1.8, amps flowing in, okay? And if you look at this situation right here, when here the current is 1.8 amps, and then it's flowing through R2 and R1, they are arranged in parallel. So I can maybe, put it like this over here, okay? Something like this. Remember, this is your R1, this is your R2. You have 1.8 amps going in, okay? And then we can, R1 is how much? R1 is 5 ohms, and then R2 is 4 ohms, okay? So let's find out the current across these two resistors, okay? So again, we can apply current divider rule. I'm going to start off with I1. I1 is equals to, first maybe we can do is total, find out the total resistance. Total resistance, because these two are in parallel, so it's going to be 5 times 4 is 20. 20 plus 20 divided by 9 is going to give you 2.22, right? 2.22 ohms. Okay, so I1 is going to be total current, which is this current 1.8 amps, times total resistance, which is 2.22 ohms, divided by the uh, component across which you are trying to find out the voltage, which is R1 in this case. R1 is 5. So if I do the math here, 2.22 times 1.8 divided by 5, so I get about 0.8 amps, okay, roughly. So if I have 1.8 volts coming in, 8 amps coming in, okay, zero point 0.8 goes here. That means 1 amps goes over here, correct? All right, so here, this right here is going to be 0.8 amps. Okay, so here you get 0.8 amps. And then the current that goes through R2 is going to be 1 amps, correct? Okay, so if you look at this node right here, current entering, you have 1 amp going in and then 0.8 getting in. So the current going through R3 will be a sum of this current and this current. So I3 is going to be sum of I1 and I2. So I get what? 1.8 amps. Okay. Okay. And the direction is actually going this way. So I'm going to have this. If you look at I1, the current is going to go this way. So I can have this direction over here. And then similarly, I got the direction for I4 over here already. Okay, all right. Now let's move on to, remember we have VA here and then we have VB here. We have to find out the potential across those. We also know that this is, since this is going to be connected to ground, so the potential over here at this node is going to be 0 volt. Okay, and because I know the current across R4, I can simply apply Ohm's law and find out uh, VB there. So I4, which is the current flowing 3.2 amps, I4, okay, equals to, and say if I just label this VC, that's connected to the ground, VC, and I4 is the potential difference between VC and VB. So it's going to be VC minus VB. And the reason it's VC minus VB is because if you notice the direction of the current, it's actually upward, right? So this is going to be VC minus VB over R4. R4 is equivalent to 8 ohms. So you got 8 here. VC is 0, minus VB. VB is going to be something that we are looking for, correct? We need to find out. I4, we have already determined that, and it came out to be 3.2 amps. Okay, so just plug in that value in there, and then if I plug in the value I4, if I do the math here, VB will basically equals to negative 25.6 volts. Okay, so VB I can rewrite here. VB equals to negative 25.6 volts. So here, this is going to be VB equals to negative 25.6. Okay, remember we have 5 amp going here. The current going in here is 3.2 amps. Okay, we had a 1.8 amps going in here. This was 1 amp, and then this current over here was 0.8 amps, and this was again 1.8, because the current entering node was 0.8 and 1, so that gives you 1.8 amps. Okay, similarly, just like how we calculated VB, we can also apply Ohm's law to find out VA here. Remember VA, which is just gonna be over here, okay, at this node, is the potential difference VC, which is ground, connected to ground. Okay, so you have 0 volts. And notice, because the current direction is like going this way, so VC minus VA, I2, the current which is 1 amp, remember this is I2, okay, this is I1, I4, which is 3.2 amps. Okay, so I2 equals to VC minus VA over R2. R2 is how much? 4 ohms. So you have 4 ohms here. Let me write it in symbolic form here first. So this is R2. VC is 0. VA, we are looking for it. R2 is 4 ohms. I2 is, yeah, I2 was 1 amp, right? I2 was 1 amp here. So that gives me this equation. VA is going to be minus 4 volts, correct? Right? I2 being 1 amp. This was 1 amp. Okay, 1 amp equals to I2. So that gives me VA equals to minus 4. So I think I have now almost everything. I just need to box the values just like I had it over here. So I'm going to do it for the second part, and then we will just add the two. Okay, so here is the circuit. Now we're going to add the two values here. Okay, restoring the two voltage sources, the two power sources. We had a one voltage source here. We had a one current source over here. Remember, this is your R4. Okay, so you have I4 here. You have I2 here. You have VA here. You have VB here. You have I3 over here. I1 over here. If I look at VA, VA is 24 here, and then VA is negative 4 here. So we get what? 24 minus 4 gives you 20. So I get 20 volts here. Okay. Now remember, you got 60 volts over here. Okay. So if the voltage here is 20 volt, that means the voltage drop here is 40 volts. Okay, now, so if I look at I4 over here, I4 is 3.2 acting in the upward direction, and then I4 over here is 1.2 acting in the downward direction. Obviously, there's more pressure over here in the upward direction, so the direction of the current would be like this, and then 1.2 minus 3.2 here is going to give you 2 amps. So if you have 5 amp here, right, 2 amp goes in here, which means 3 amp will go in this direction. Okay, now let's check for I2 here now. Okay, I2, we had 1 amp in the upward direction, and then over here we had 6 amp in the downward direction. So there was more pressure acting downward. So that would mean the difference here, 6 minus 1, right? 6 I2 and I2 here would be 5 amps. So the current flowing across this resistor will be 5 amps and the direction will be downward. Okay, so remember, again, I can just go through it real quick. If you look at your I2, 1 amp direction upward, okay, and here I2, 6 amp direction downward. So there's more flow charge going down. So therefore, the direction of the current is going to be downward. You have 5 amp coming here. So that means you will have a total of 8 amps over here, okay, to this node. You have 3 amp coming in here, you have 5 amps coming here. So that gives you 8 amps over here. Now let's move on to I1. So if you look at I1 here for the first part, we had 7.2 amps. And then over here, we had I1 0 0.8 amps, and they both were acting in the same direction. So 7.2 plus zero point 0.8 gives you 8 amps here. Okay. And that's what we had over here too. So that's good. 8 amps. We have 5 amps going in here. That means you will have 3 amp going in this direction. Okay. So your I3, and also you can prove it over here. You had your I3 from the second part, 1.8, okay, and then here I3 1.2, right? And they both were in the same direction. So if you add 1.2 plus 1.8, you get 3 amperes, right? And that's what you had over here. And I just wanna mention here, this VB that we had calculated over here, VB here was negative 25.6, and you had a 9.6 over here. If you add them up, you get 16, but it's going to be in negative and not in positive. And so remember that there's more pressure acting over here on this part of the circuit uh, moving along. Okay, and then this will go here, here. Again, remember you got uh, 3 amp coming over here to this node. You have 2 amps coming over here. 3 plus 2 gives you 5 amp, and that's what you have over here. Okay, all right. Also, I did the simulation here, and you can see that our results are pretty consistent than what we got here also. So 8 amp going in. On the left, you see 60 volt battery. There's a 40 volt uh, voltage drop across R1, which would mean VA would be 20, and then VB is negative 16 that you see on the right. You have 5 amps going in, acting downward, and then you have 2 amp going up across R4, 36 volt across the resistor R3. You have 5 amp going, acting downward across R2, which is 4 ohms, and then also 3 amp across R3, which is 12 ohms. Okay, so that's superposition for you. Uh, I know there was a lot of math in there, a lot of equation. Uh, it's a tedious task to get it done, but hopefully you enjoyed it. Thank you for watching. Bye.